Hello, good day. This is Dan Burnett from Surface Measurement Systems. I am currently the head of the science department at Surface Measurement Systems. I'm quite happy to introduce the speakers for today's webinar. Dr. Joanne Lee from Imperial College London will be the first speaker today. She is currently a research associate in the Future Materials Group at Imperial College London, focusing mainly on cellulosic materials research. During her PhD work, she explored bacterial cellulose, in particular, and its application as coatings on woven fabric for enhanced particulate filtration efficiency. So please join me in welcoming Dr. Lee, and the floor will be hers. She will give the first presentation, probably we should take questions and answers at that point from the first talk. And then Dr. Annette Condor will give the second presentation, and we'll open the floor for question and answers during that session as well. So thank you very much for your time and attention, and we're looking forward to hearing our two excellent talks today. Dr. Lee, the floor is yours.
Thank you. I'll just share my screen for now. Great. Yes, so good afternoon, everyone. I'm Joanne once again from Imperial College. So I would first like to thank Anna and John for this invitation today and allow me to share with you my PhD research about low grammage nanocellulose coating for woven fabric, especially on the topic of dispersion of bacterial cellulose in different organic solvents and the use of solubility parameters. So for today, I would like to start with some background of my PhD research and why are we interested in dispersing bacterial cellulose in organic solvents, followed by determining the surface energetics of bacterial cellulose with inverse gas chromatography, which is the collaborative work with surface measurement systems, and last, how Hansen solubility parameters play a role in this work. So to start with, my PhD project is mainly surrounding the addition of nanocellulose to protective clothing for enhanced particulate protection. So here is a typical protective garment which offers thermal protection to military personnel and exposed to chemical warfare agents. And for a typical protective garment, it usually has a multi-layer construct and is composed of the shell fabric layer in front and an activated carbon layer at the back for vapor and aerosol protection. But as you notice, the shell fabric layer has an open weave pattern, which almost gives no particulate filtration protection to the garment, and it leaves the carbon layer behind very susceptible to damage. Besides, the current design of the protective garment still imposes certain physiological burden on the user, and it is very sweaty and very uncomfortable after a prolonged time of wearing. And inspired by the wide application of nanocellulose in water purification membrane, here we are thinking to coat a very low grammage of bacterial nanocellulose, which will then form a nonwoven network on the shell fabric surface. We hypothesize that the nanocellulose can form a network inherited with pores in the nanometer range, and that the hygroscopicity of nanocellulose will allow the passage of moisture through the fabric, thus achieving an improved aerosol particulate filtration efficiency of the protective suit without adding physiological burden to the user. And for coating, here we're adopting a simple procedure where the bacterial cellulose pellicle are first blended in water and the bacterial cellulose suspension are then vacuum filtered onto a woven fabric substrate to obtain a bacterial cellulose coating of 3 different grammages, with the highest coating grammage of only 1 gram per square meter. And these samples are then oven dry at 120 degrees for 30 minutes. And from these SEM images, we can observe that a nonwoven bacterial cellulose coating is deposited on the fabric surface, closing the inter-yarn pores of the fabric substrate. We then test these bacterial cellulose coated woven fabric samples for the air permeability with a benchtop device and the particulate filtration efficiency with an in-house built wind tunnel, where in the wind tunnel, we'll place the testing sample in the middle of the wind tunnel, and during testing, sodium chloride particles will be generated as a challenge particle, and the ratio of sodium chloride mass concentration upstream and downstream of the sample will be taken as the particulate filtration efficiency. And with the bacterial cellulose coating layer that closes the pores between the yarn, we expect that the particulates in the flow will be captured with a size exclusion mechanism, and filtration efficiency against PM1 particulate increased from that of 11% of an uncoated fabric to a maximum of 85% when 1 gram per square meter of bacterial cellulose is coated. And this increase in particulate filtration efficiency, of course, is accompanied with a reduction in air permeability. But it is also shown here that the water vapor transmission rate remained constant and is not impeded upon the addition of bacterial cellulose, mainly because of the low grammage that we are using and the hygroscopicity of the bacterial cellulose in itself, which is very beneficial to us as it shows that the transpiration of sweat will not be compromised when this bacterial cellulose coated fabric is being worn. So by far, we have proved that a robust and a low grammage of bacterial cellulose coating can be vacuum filtered onto a woven fabric to enhance its filtration properties without compromising the moisture permeance across the protective garments. And if you have noticed, we have been only using water as the filtering medium all this time, as this is an easy and obvious choice given the hydrophilic nature of nanocellulose attributed by the hydrogen bonding between water and the exposed hydroxyl groups. However, we are also aware that the current bacterial cellulose coating layer is not perfect. For instance, we can observe that agglomeration of bacterial cellulose in the suspension state, especially when we compare it with the cellulose suspension from other sources. And these agglomerations then lead to pinholes or defects in the resulting coating layer and subsequently cap the particulate filtration efficiency of the resulting coating layer at the maximum of 85% for PM1 particulates. We're thus very curious if there's a way to optimize this system and improve the dispersion of bacterial cellulose in suspension. And as we're looking through literature, we realize that there is a small but growing numbers of isolated publications that highlight the amphiphilicity of cellulose and that nanocellulose could also be well dispersed in selected organic solvents. We therefore are interested if other organic solvents would be a more suitable dispersing media for bacterial cellulose, and would this better dispersion of bacterial cellulose hence improve the quality of the coating layer and result in an improved filtration efficiency. And to study this, here we have dispersed bacterial cellulose in various selected solvents by solvent exchange, namely ethyl acetate, acetone, and a series of ethanol-water mixture of different Freudian ratio. And similar to our previous experiments, the bacterial cellulose suspension from different solvents are then vacuum filtered onto a woven fabric substrate at 3 different grammage and oven dried. And first, by inspecting the visual appearance of the dispersion containing bacterial cellulose, it can already be observed that the dispersion quality of the bacterial cellulose in various organic solvents are indeed different. Agglomeration can be easily observed in the ethyl acetate and acetone suspension because of the sulfophobicity of bacterial cellulose in these 2 solvents. And a more homogeneous suspension can be observed when ethanol-water mixture or water is used as the dispersing media. And the coverage of bacterial cellulose nanofibers with a coating grammage of 0.5 gram per square meter are also shown here. And consistent with what we observed earlier, the agglomeration of bacterial cellulose dispersed in both ethyl acetate and acetone result in a very poor bacterial cellulose coverage of the underlying fabric substrate, where we are still seeing bare and uncoated yarns, and the pore opening between the yarns remain open. However, when the bacterial cellulose coating was applied from a more homogeneous bacterial cellulose dispersion, a better bacterial cellulose coverage and hence less defects are resulted. But very unexpectedly, we also noticed that the bacterial cellulose coating applied from BC in water dispersion does not possess the highest coverage. But in fact, the BC coating applied from a BC in 60% ethanol-water dispersion has the highest coverage, whereby all the pore openings of the woven fabric are fully covered. So this difference in bacterial cellulose coverage is further supported by the filtration properties result, where the bacterial cellulose coating applied from a 60% ethanol-water mixture has the highest filtration efficiency. inferring that there is a better dispersion of bacterial cellulose in ethanol-water mixture than water, which result in a more homogeneous coating. But the question remains as why we are observing this and why would this happen? So to investigate this observed difference in the quality of bacterial cellulose coating produced from different dispersing media, the surface energetic of bacterial cellulose was first quantified to ascertain its interaction with water and other organic solvents. So generally, the surface property of a solid are described by a dispersive and a specific component, where the total surface energy of a solid surface is the sum of the two. And while contact angle measurements are typically used to determine the dispersive and specific components of a solid surface, this method is not very suitable for bacterial cellulose, as we couldn't produce a sample that is flat and non-porous. And here is where we collaborated with surface measurement systems, and we use inverse gas chromatography, or IGC, to determine the surface energetics of this cellulosic material. So the surface energetic of bacterial cellulose at infinite dilution was first determined, and by knowing the retention volumes of different N-alkane probes, the dispersive components can be calculated and determined from the linear slope of this plot on the right. And the dispersive component of bacterial cellulose was measured to be around 60 millijoules per square meter, which is very similar to values reported by others in literature. And on the other hand, the specific component of the surface energy of bacterial cellulose can be measured with a pair of monofunctional acidic and basic probe molecules. So here we're using ethyl acetate and dichloromethane as the acidic probe and basic probe respectively, and the specific component of the surface energy of bacterial cellulose is measured to be around 6 millijoule per square meter. But despite knowing the dispersive and the polar components of the surface energy of bacterial cellulose, it still didn't add much to our understanding of why bacterial cellulose are better dispersed in ethanol-water mixture than water alone. And further information is required to answer this question. So here we are then referring to the theory of solubility parameters. Solubility parameters has been a very useful tool in interpreting the miscibility and compatibility between materials and is widely used in the polymer and pharmaceutical industry. Solubility parameters is related to the cohesive energy density, and according to Hansen, it can be divided into three different components. The first being the dispersive component, which represent the contribution of van der Waals forces. Next, the polar components, which describe the electrostatic interaction between dipoles and are based on the overall dipole moment of the molecules. And finally, the hydrogen bonding component, which describes the specific interaction involve a directional bond between a H donor and an acceptor. And as a rule of thumb, the more similar the Hansen solubility parameter between two components are, the more compatible they will be. So to indicate how close the solubility parameters of two components, in our case, bacterial cellulose and the respective solvents, are to each other, the solubility distance can be calculated with the equation shown here. And while the components of solubility parameters of different solvents can be found very easily from different databases, the solubility parameters of bacterial cellulose is seldom reported. So here we're using an indirect method to estimate the solubility parameter components with the aid of inverse gas chromatography. By using a series of test probe molecules and by linear regression of the retention volumes at different temperature, the partial solubility parameter of bacterial cellulose can be estimated to be around 19 for the dispersive components, 25 for the polar components, and 26 for the hydrogen bonding components. So taking these numbers further to calculate the solubility parameter distance, it can be seen that the value of solubility parameter distance is the lowest for the 60% ethanol-water mixture. This indicates that the solubility similarity between bacterial cellulose and these specific solvents and confirm our earlier observation in filtration properties by experiments. So in short, today we have demonstrated that there's a very strong agreement between the solubility parameter distance and the filtration properties obtained experimentally, and suggest that the use of solubility parameter in understanding bacterial cellulose dispersion and material processing will be helpful. And that's the end of my presentation today. I'm very happy to take any questions. And if you'd like to have more details on this work, you may refer to our recent publication in carbohydrate polymers. Thank you.
Thank you, Dr. Lee, for the excellent presentation. Maybe to get things kicked off, I was just curious, do you think that what would be a bigger factor, the loading or the solvent that you use? So could you overcome some of the challenges with less solvent? I mean, with changing the loading of the bacterial cellulose in suspension, or do you think the driving force would be the solvent used to get good coverage?
Basically, we're trying to keep to use a very low grammage so that the non-woven layer won't be too thick to stop any water or air passing through. But it do plays a role too. So from our experiments result, we can see that if we're using the 60% ethanol-water mixture as our solvent, because the dispersion quality is much better than just water, we can achieve the same filtration property when using only half of the cellulose that we need in water. So upon 5 grammage of cellulose coating from a ethanol-water mixture will perform the same as a 1 grammage coating from water. Would that make sense?
Yeah, no, thank you. I mean, it would look pretty clear to me, but I just wanted to ask about that. We do have a question from one of the. Have you measured the pore size distribution and/or specific surface area of the coated films?
We have. The thing is, the woven fabric itself is so porous that it masks almost all the change after we add the bacterial cellulose coating. So it's not very representative, and we didn't include it here in the presentation, but it's in the publication itself.
Okay.
Yeah.
Thank you. Let's see, are there any other questions? Let me make sure I'm in the right area in the chat. I'll wait another minute to see if there's any other questions. Okay, here's another question. What temperature range was used in the IGC for bacterial cellulose for measuring the properties you measured?
I think we're using, just to be sure, 30 to 45, if I'm not wrong. 30 degrees to 45 degrees.
Okay, thank you. That was for the solubility parameter, correct?
Yes.
Yep. Okay. Well, it looks like we may have answered the questions to date. If there are further questions that come in, maybe later on, I'll ask at the end of the second presentation. So I want to thank Dr. Lee for your very nice presentation today, and we will move on to Dr. Condor's presentation. So Dr. Annette Condor is the IGC SEA Product Manager and Product Specialist for Surface Measurement Systems. Annette has been working with inverse gas chromatography techniques since 2005. She started her work in this area as a chemical engineering at the University of Panoa, Hungary, where she received her MSc in chemical engineering, accredited by the British Institute of Chemical Engineers, and her PhD in chemistry and environmental science. She published several research work in peer-reviewed journals, collaborating research groups around the world, including the likes of Deakin University, Composite Innovation Center in Canada, TSAC in Ireland, Boku University in Austria, Liverpool, Johns Moore in the UK, Givaudan in Switzerland, and so on. Her research interest lies on the surface characterization of different solid materials and improvements in inverse gas chromatography technique. So with that, I thank Annette for her time today. And I will turn the floor over to Annette for the second presentation in today's webinar.
Have a good afternoon and good morning to everybody. Thank you, Dan, for the introduction, and thank you, Joanna, for this excellent presentation. During my presentation, I will just briefly introduce the inverse gas chromatographic technique, what we used to measure the surface energy and solubility parameter for Joanna's samples, and also for some polymer samples in my case. And then I will show you some details about the solubility parameter analysis using IGC, and some data on polymers we are working on recently. So inverse gas chromatography is a relatively old technique, although it's still new in material science. The reason is that because when the technique was developed in the 60s, there was no commercial device till 2000, when SMS released the first IGC instrument. And then in 2009, the first purpose-built inverse gas chromatography was released by SMS. So during that time between the development and the release of the first commercial device, people just build their own IGC instrument using a GC system as a base. And if there's no commercial device, needless to say that there's no sales or no marketing behind the instrument, the product. And also the World Wide Web wasn't available for so long, and it's hard to get to know the technique if there's no such a promotion behind. So that's the only reason why it's still relatively new, and the technique is really powerful for powders and fibers. So if you want to measure surface energetics of a powder or fiber, IGC is really the best tool technique to use, because it overcomes the difficulties what contact angle has on those type of materials. IGC SEA system is designed to measure the surface energy heterogeneity of solids. Nevertheless, it's suitable to measure other physicochemical properties of solids, for example, adsorption isotherms, heat absorption, glass transition temperature, and the solubility parameter, which is the topic of this webinar today. Inverse gas chromatography is very similar with the classic analytical gas chromatographic system. That's why a gas chromatographic system was a good base to use and to convert for inverse gas chromatographic application, because both technique is a gas solid chromatographic device. The difference is that in case of inverse gas chromatography, the solid phase is our sample of interest. So we pack a column with our solid material we'd like to investigate, characterize, and then we inject through this column different organic vapors, pure organic solvents, one by one, measuring the retention time of all those different organic vapors, and the different physicochemical properties of the solid can be determined, because the retention time of the different organics on the solid surface will indicate the interaction strength between the injected probe and the solid materials, which is in the column. The columns a little bit different compared to the classic GC columns, so not just in length. So the column we use in IGC SEA system is a 30 centimeter long column. So they are not that long as in case of the analytical GC systems. And we provide different column diameters for the different types of samples, for the different morphology samples. And also we have these columns in different materials. So we have a silicized glass, quartz, and stainless steel tubes. to use. Analysis with IGC system is a non-destructive analysis. So once you pack a column, you can run different types of measurements and determine different properties of your solid material. IGC is engineered and designed only for inverse gas chromatographic application to measure thermodynamic parameters, and therefore we have different types of parts in the system. Especially the oven is not a big squared oven like in case of the normal GC. Our oven is like a direct column, use a direct column heating. There's two column position. You can see the heating element surrounds the column in order to get stable and constant temperature along the column, which is very important when you measure thermodynamic parameters, to keep the temperature stable and constant during the measurement, because it can affect the results. To measure the different thermodynamic parameters, we also have to inject a small amount of organic vapors. In order to inject the smallest amount, we designed a special gas phase injection system. It's similar to the head phase injection in GC systems. This one also injects from the gas phase. It allows us to inject a very small, tiny amount of vapors. And this special injection system has a SMS patent. And we also provide a very useful tools with the instrument to enhance column packing and preparation of the samples. On this slide, you can see just the basic specifications of the instrument. The carrier gas in the system can be helium or nitrogen, depending of the needs. And there's two column position, the column oven temperature range, depending of the configuration, can be 20 to 500 degrees Celsius. And our IGC SES system equipped with flame ionization detector, because it's the most sensitive detector for organic vapors and it's not sensitive for water. So we can provide the instrument with the background humidity controller, which allows you to measure the impact of the relative humidity on the different surface properties, which is a very useful feature of our IGC instrument. I think it's one of the main benefits of the instrument, because there's humidity everywhere during production, during the application of solids, during processing, and how that humidity can affect the different properties, surface properties of solids. It's really important to know, not just for development, R&D, also for batch-to-batch variability. And the instrument can measure different properties. The list of the different physicochemical properties are on this slide. I already mentioned some of that. The surface energetics, the different part of the surface energy, heat absorption, acid-base constants, BT specific surface area, and so on. So the topic of this webinar is the solubility parameters. And if you are familiar with the solubility parameters, probably you know there's different theories, different methods. One is the Hildebrand, the classic Hildebrand solubility parameter concept, and the Hansen solubility parameter theory, which, as Joanna mentioned, contains three different contributions of the solubility parameter. But first of all, yeah, solubility parameter is really a useful parameter to see that which solvent will be the most compatible to your solid to dissolve, and also it's used for in pharmaceutical industry for dispersion studies. The Hildebrand parameter is just express the total solubility parameter. It also correlates with the cohesion energy density of the solid. And if you measure the solubility parameter, the Hildebrand solubility parameter of your polymer or your solid material, then it's very easy to determine that which solvent will be the best choice and which is not, because based on the theory, the 2 megapascal root square difference plus minus tells you that which solvent is the best, so and which is not. So anything which is which has a solubility parameter higher or lower than your polymer with the 2 megapascal root square is not the best solvent. We measured this Hildebrand solubility parameter of a PMMA sample. You can see the results on this slide. We have an application note about it. It's available on our website. What we measured, 19.08 root square megapascal, is very close to the literature values we found. And those literature values were mainly calculated values based on group contribution methods. So the difference is that it's very normal. The Hansen solubility parameter set contains 3 components. So one of the first is the dispersive contribution of the solubility parameters. The second is the polar, and the last is the hydrogen bonding part of the solubility parameter. And these 3 components gives the total solubility parameter, the total Hansen solubility parameter. To determine this with IGC system, you need to use different types of solvents in order to measure the different interactions on the surface. And typical solvents for hydrogen bond interactions are the alcohols, and pyridine, for example, for polar, different aromatic hydrocarbons and ketones. And for the dispersive, it's the easiest one, it's the normal alkanes. So once you injected all these different probes, the software automatically provides you the 3 components of the Hansen solubility parameter. It's important to mention that these the Hansen solubility parameters and the Hildebrand solubility parameters analysis has to be performed at the glass transition temperature of the polymer or the solid material. So it makes the applicability of the analysis a bit limited, especially in case of polymers or some materials. But in case of Hansen solubility parameter, the same concept as in case of Hildebrand. So once you measure the solid solubility parameter, there's a specified radius distance from that point, and every solvent which is in that sphere will be a solvent which is miscible with your polymer or solid, and everything outside will not. And the last model, the last calculation, which is also implemented into our software, SCA software, is this model from Snyder and Karger, which is based on the adsorption energy of the different probes. This calculation also provides you the three components, the dispersive, the polar, and the hydrogen bond component of solubility parameter. But this type of application allows you to measure the solubility parameters at below the glass transition temperature or above glass transition temperature. So any temperature range where you are interested in the solubility parameter. You have to inject a series of different solvents, and the software creates this matrix and determines the components of the solubility parameter of your solid using the injected solvent retention data, adsorption energy, and which is measured, and the solubility parameters of those solvents. To select the best solvents for the analysis is probably the most difficult part of the measurement, because not always there's no standard solvent set for every solid. But if you use the extreme probes like strong acid, strong basic, and the typical alkanes, you are fine. But for example, for PEG sample, which interacts very strongly with alcohols, but less with alkanes, in this case, different alcohols recommended than alkanes in general. And finally, I'd like to show you some solubility parameter results on recycled polymers we are recently working with, which is a very important topic, as many countries are trying to recycle more polymers to reduce the waste on the landfill. And to find the best solvent for this polymers, for this type of polymers for the recycling process, to separate the different pigments and different particles from the polymers and to recycle them, it's really a challenging part. And the solubility parameter can help them to find the best solvent. We receive different recycled polymers. One is from an industrial plant, and we have also 4 samples from Imperial College. One is a virgin HDPE sample, and then we have 3 samples where Imperial College simulated the recycling process 10, 20, and 50 times. And we are working with these samples right now. And at the moment, we already have the recycled HDPE polymer sample solubility parameters. This HDPE sample is what we received from industry, and the solubility parameter what we measured is 13.64. As you see, it's a bit far different from the literature values, but that literature values, what we found, that value is a calculated value, so it's not really represent the recycled HDPE, which can contain a lot of different materials as well, so like different colorants what they use for these samples, different pigments or metals, and all sorts of things which also affects the solubility parameter. So we were not surprised by these differences between the literature value and the measured value of this HDP sample. And we are still working on the other samples to get the solubility parameter, but we have a good trend on surface energy, because also we first measured the surface energy. I think it's just this I did as a last slide. So the trend is quite clear. So the virgin HDP has quite high surface energy, and then the 10 and the 20 times recycled shows decreases in surface energy. But then the 50 times recycled HDP has again a little bit higher surface energy, whereas the additional measurements, some rheological and other data showed there's more degradation happening. So these are the results so far, what we have on polymers. And thank you for your attention, and I'm happy to answer your questions if you have any.
Sorry, I was muted there. Thank you very much, Annette, for the presentation. I do have one leftover question for Dr. Lee, if she's still available. They were asking how, on the surface energy values, how was a surface coverage of 0.02 was decided due to that they were assuming that the surface energy was heterogeneous. So maybe you can comment on the heterogeneity and you know, maybe why that particular value was chosen to use.
Yes, so for that surface energy, we're mainly looking in the infinite dilution range, because that's in the Henry law region, so it's not affected. So it's still a linear relationship, but then on the heterogeneity, we did saw some heterogeneity on the surface. So for the total surface energy, it drops from around 70 to 60 from 0.005 coverage to 0.02 coverage. Yeah.
Okay, thank you. Moving on to Annette's presentation, just a general question about Hansen solubility parameters. I mean, in general, what other are some applications outside of what you've shown today? You know, what are some other case studies or uses where you've used Hansen solubility parameters for different systems or applications? Or where might these also apply to?
It can be used, pharmaceutical industry also use these parameters, because it correlates with the release rate of the drug particles, and they also use for other formulation or other studies as well. So pharmaceutical industry is the other which use Hansen solubility parameters, polymer industry, and also in coatings. So for pigments and for these type of samples, also to find the best dispersion media or the solvents. They use also. There's nothing else in my mind, but then maybe if you
Okay.
have any examples also.
Yeah, thank you. That's a good summary. You mentioned that selecting the right solvents is critical for this application. Are there any tips or tricks or suggestions of where to start? Do you look at overall solubility or miscibility of a polymer with a solvent, or is there anything that you would recommend for people looking to choose the right solvents to use for the different components of the solubility parameter for the Hansen?
Good question. So for the dispersive component, alkanes, minimum 3 alkanes I suggest, and not really. Also, in case of solubility parameters, they can use every second, so like hexane, octane, and decane to cover a wider range of alkane chain. And then for polars, I would suggest some extreme ones, so strong acid and strong base. We have a table in our instrument manual which shows the acceptor and donor numbers of the different polar solvents, so you can see that which is a strong acid and which is the strong base. So based on that, you can choose the best solvent. And for the hydrogen bond, also again, minimum 3 solvents needed to get this parameter accurately. And I would just use yeah, couple primer alcohols and one isopropanol maybe. That's all. Yeah, it's not easy. That's the challenging part. So I always inject more solvents. So, and then once I see that one of the solvents didn't show any interactions on the surface, I just exclude it. And then I will still have enough solvents to get all the different components. So I would inject more than which is the minimum or required. It also depends of time what they have.
Sure.
So.
Well, thank you. That's that's a good place to start at least. So yeah, I don't see at the moment any other questions in the chat right now. Obviously, if there's things that come after the fact, you're welcome to email Surface Measurement Systems. You can email us science@surfacemeasurementsystems.com. You can also go to our Adsorption Hub, www.adsorptionhub.com. If you don't have access, you can request access from your local salesperson. We do upload our older webinars on here, so eventually this webinar will be uploaded there. You can also contact us there for looking at the Adsorption Academy if you want to learn more about the science behind our products. You can also get technical support and sales support there as well. So without further ado, I guess I'll want to thank once again Dr. Lee and Dr. Condor for their presentations today. We very much appreciate your time and contributions. And I want to thank you for your time for the audience for participating in this webinar. And with that, I'll turn it over to John to close it out.
Thank you, Dan. Yes, thanks once again to our speakers, Dr. Joanne Lee and Dr. Annette Condor. And of course, thank you to Dr. Dan Burnett for being here to play our host today. As mentioned, if you have any follow-up questions, please contact us at science@surfacemeasurementsystems.com. This webinar will be available to view on our website and on the Adsorption Hub, along with a large collection of courses, application notes, and reference materials. It's all free to access on the Adsorption Hub, so please go to www.adsorptionhub.com. You can place a request there, or if you're one of our users, you can request your local salesperson and they can get you set up. Thank you all again for joining us today, and we hope to see you soon.